In this lesson, we discuss sigma notation and limits of finite sums. In a previous lesson, we were studying how to approximate the area underneath a curve, and we were using rectangles. We were using an upper sum, we used a lower sum, a midpoint sum. And the thing is, the more rectangles we use, the more accurate our approximation became. The issue we have, though, is how do we approximate this sum for many, many, many rectangles? We even looked at what the sum was approaching as we considered 1,000 rectangles. So in this lesson, we will study how sigma notation can help us consider what happens as the number of terms, the number of rectangles, if you will, approaches infinity. So let's dive into sigma notation and its properties, and then we will see how sigma notation helps us with finite sums. So with sigma notation, this is the capital Greek letter sigma, which means sum. So if I use this sigma, if I use this letter, it means I'm adding something. So I would be adding, let's say, a sub k as k goes from 1 to n. And so what this sigma notation means is that you are adding this expression over and over again, and you're letting k run from 1, starting at 1, all the way through n. So in other words, it'd be a sub 1, that's where we start, plus a sub 2, plus a sub 3, plus etc., plus a sub n minus 1, plus a sub n. So it is adding a bunch of terms, and you're letting this value here, this subscript, start from 1, and it doesn't always have to start at 1. You start at whatever this value is here, and you go all the way through this upper limit. K in this case is called your index of summation, and this right here is telling you that your index starts at k equal to 1 and goes all the way through until k is equal to n. Now, this value, again, the index of summation does not have to start at 1. It's most commonly it starts at 0 at 1, but it could start at any value. And the letter chosen to represent your index of summation doesn't have to be k. But the letters most commonly used are I, J, and K. So let's look at some examples of sigma notation, and let's make sure we understand what they are in expanded form. So the sum of k as k goes from 1 to 5 would basically be 1 plus 2 plus 3 plus 4 plus 5. And this sum is 15. Okay, so this is a series, right? This is a series, or it's the sum written out one term at a time, right? This is the series. This is the value of the sum, and this is the sum in sigma notation. So you can see sigma notation is shorthand for writing 1 plus 2 plus 3 plus 4 plus 5. We don't want to write all of that out all the time, so this is shorthand for expressing all of this. Let's look at another example. So the sum of -1 raised to the power of k times k as k goes from 1 to 3. So let's expand this. This would be equal to -1 to the first power times 1 plus -1 squared times 2 plus negative 1 cubed times 3. So then this would be negative 1 plus 2 minus 3, which is negative 2. So negative 2 is the value of the sum. This is the series, and this is sigma notation. Let's look at another one. So we have the sum of k over k plus 1, and we're letting k go from 1 to 2. I would actually invite you at this point in the lesson to pause the lesson and see if you can come up with this sum on your own. Go ahead and pause the video here. All right, so then this would be 1 plus 1, 1 over 1 plus 1, plus 2 over 2 plus 1. And we stop there because k only goes from 1 to 2. So then this is 1/2 plus 2/3, which is 7/6. Awesome. Let's do one more. Let us consider the sum of k squared over k minus 1 as k goes from 4 to 5. You see, we don't always have to start at 1, all right? So then this written out here would be 4 squared over 4 minus 1 plus 5 squared over 5 minus 1. If I continue to simplify, this would be 16 thirds plus 25 fourths, which is 139 twelfths. This is the sum here. Now let's go in the other direction. What if we are given a series and we're asked to express the series in sigma notation? So in other words, if we're given 1 plus 3 plus 5 plus 7 plus 9, right? That's a series. And notice this is the sum of odd numbers. There's different ways we can write this. And I think a lot of it has to do with what we allow the lower limit to be. In other words, where we allow the index of summation to begin. For example, we can write this in sigma notation like the sum of 2k plus 1. But if you write it as 2k plus 1, then you need to let k begin at 0. So you let k begin at 0 and make sure, well, you want to get all the way through until 9, so let k go from 0 to 4. And that's one way to do it. I mean, look, go ahead and plug 0 in. 2 times 0 plus 1 is 1. That's the first term. And then you would let k be 1, then let k be 2, let k be 3, let k be 4. If you plug 4 in, 2 times 4 is 8. 8 plus 1 is 9, right? So this is one way to do it. But if you want your sigma notation to start, let's say, at k equal to 1, well, then this expression here, this formula would have to be different. So it would have to be something like 2k minus 1. And let's see, if you plug in 1, 2 times 1 minus 1 would be 1, which is the first term, right? If you plug in 5, 2 times 5 is 10, 10 minus 1 is 9. So we're going to let k go from 1 all the way through 5. You see, there's different ways you can express the sum. If you wanted to start with k equal to 2, you could do that. If you let k equal to 2, then this would have to be 2k. Well, you want to get 1, right? So 2 times 2 is 4. So then 4 minus 3. There you go. That would do it. Again, letting k be 2, this is 2 times 2 minus 3. So that's 4 minus 3, which is 1. If you want to end at 9, well then let k end at 6. 2 times 6 is 12. 12 minus 3 is 9. So k is going to have to go from 2 to 6. If you wanted k to, what if you wanted, this one's interesting, what if you wanted k to begin at, let's say, I don't know, -3? Remember, you want to end up with 1. So if you do 2k, let's see what that would be. 2 times -3 is -6, right? And if you want to end up with 1, then you're going to have to add 7. So 2k plus 7, right? If you start with -3, this expression is going to give you 1. And if you want to end up with 9, then plug in 1 for k, right? 2 times 1, then plus 7 would be 9. So k is going to have to go from -3 to 1. So the point of the matter is we can write this sum. We can write this sum right up here a number of ways. And I think it all depends on what we let the lower limit be. This is your lower limit down here, 0 is, and then 4 is your upper limit. So it depends on what you allow the lower limit to be. It's going to give you the same sum. You know, all of these will give you the same sum, but how you write sigma notation is, well, it's up to you how you want to write it. We can also do some pretty cool manipulations with sigma notation. So consider the following. The sum of, let's say, k plus k squared as k goes from, let's say, 1 to 3. So what would this be? Well, this would be, let's see if I can write this here, 1 plus 1 squared plus 2 plus 2 squared plus 3 plus 3 squared. And because addition is associative, I can regroup these terms to be 1 plus 2 plus 3 plus 1 squared plus 2 squared plus 3 squared, which is equivalent to sigma, right, of k as k goes from 1 to 3 plus sigma of k squared as k goes from 1 to 3. So notice that sigma of this sum is equivalent to the sum of these sigmas, right? So in general, what we're saying is sigma, and that was a pretty sloppy sigma there. There, better. Sigma of a sub k plus b sub k as k goes from 1 to n, let's say, is equivalent to sigma, the sum of a sub k, as k goes from 1 to n, plus the sum of b sub k, as k goes from 1 to n. Here are some other rules for sigma notation. We talked about the first one already, but there's also the difference rule, which follows just from what we discovered about the sum rule. But there's also the constant multiple rule, so the sum of c times a sub k is equivalent to c times the sum of a sub k. So it's really like you can factor out that constant c and then evaluate the sum of a sub k. Also, the sum of just a constant. The c is just a constant. As k goes from 1 to n is just n of those constants. So n times c. So let's illustrate how we can use these rules to evaluate some sums. So what if we had the sum of, let's say, 3k minus k squared as k goes from 1 to n? Well, first of all, this 3 here can be factored out, But before we do that, notice that this is a difference. So then we can rewrite this as the sum of 3k minus the sum of k squared. Of course, as k goes from 1 to n for each of these. And now I can use our rules to factor out this 3. So 3 times the sum of k, as k goes from 1 to n, minus the sum of k squared, as k goes from 1 to n. So we can rewrite this difference like this. Let's look at another example. What if we come across something like the sum of negative a sub k, as k goes from 1 to n? Well, that negative can be considered to be a negative 1, so we can factor that out, like a negative 1 times the sum of a sub k, as k goes from 1 to n. What if we have something like the sum of k plus 4? Can we work on rewriting this? As k goes from 1, let's say, to 3. What would this be? Well, we can rewrite this as the sum of k plus the sum of 4, as k goes from 1 to 3. And this would be, well, the sum of k would be 1 plus 2 plus 3. That's the first sum. Plus, and then we can use one of our rules here to say, well, this is going to just be 3 times 4. So then this is 6 plus 12. So this sum is equal to 18. I like this one. What about the sum of 1 over n as k goes from 1 to n? Well, this would be equal to n times 1 over n, because this is just a constant. This expression is not dependent on k at all. So it's just 1 over n times. So this is equal to 1. Now, there are some really, really popular formulas using finite sums. Let me show us a few. The first one is the formula for the sum of the first n integers. This first formula for the sum of the first n integers is actually said to have been discovered by Gauss, by the mathematician Gauss, at a very young age. I think rumor has it that Gauss was around 8 years old when he discovered this formula. There's also these two formulas which are really helpful, the sum of the first n squares and the sum of the first n cubes. And we can use finite sums, sigma notation, for these formulas. So this is really, really helpful. Now that we've spent some time talking about sigma notation, we're going to see how this is going to help us tackle the problem that we looked at in an earlier lesson. So let's go back, let's circle back to this problem. Find the limiting value. We say limiting value because we're going to take a limit. Find the limiting value of lower sum approximations to the area of the region R. Let me label our region here, R. So this is the region R that we are looking to calculate the area for. Below the graph of y equals 1 minus x squared, and above the interval 0 to 1 on the x-axis, using equal width rectangles. So we did this before. In an earlier lesson, we drew 2 rectangles, and then we increased it to 4 rectangles, and we saw that the approximation became more accurate the more rectangles we used. And we want these, now here we go, we want the widths of these rectangles to approach 0. In other words, we want these rectangles to become more and more and more thin or more narrow, and whose number approaches infinity. So we want infinitely many rectangles so that our approximation, our lower sum, in this case they want a lower sum, approximation becomes as accurate as possible. So the idea here is that we're going to use n number of rectangles, okay, of equal width. Now, if you remember, the width of each rectangle will be represented with delta x, right, the change in x, and it will be, do you remember we wrote it as b minus a over n? Well, in this case, since your interval is 0 to 1, it'll be 1 minus 0 over n, that is to say 1 over n. 1 over n represents the width or the base of each of our rectangles. Now, what we're going to do is we're going to see what happens as we let n, the number of rectangles, approach infinity. Approach infinity. All right, so if this is the width of each of our rectangles, then our interval from 0 to 1 is being subdivided into sub-intervals. Now, these sub-intervals have equal width. And so let me see if I can list them out here for us. So here are the sub-intervals, okay? Let me come over here. The first interval will start at 0 is the left endpoint, right? And then remember, the width of each of our rectangles is 1 over n. Therefore, the right endpoint would be 1 over n. So this is the first subinterval. The next subinterval, the left endpoint is 1 over n. And then remember, the width is 1 over n. So you would add 1 over n to 1 over n. 1 over n plus 1 over n is 2 over n. So 2 over n is the right endpoint. The next subinterval, this is the third subinterval, would be 2 over n, that's the left endpoint, plus 3 over n. Etc. Comma. So you can hopefully see the pattern here. The last interval will, of course, the right endpoint will be 1, right? And then the interval the left endpoint of that interval, rather, would be n minus 1 over n. And the right endpoint is 1. 1 written as n over n. So these are all of the sub-intervals. Each subinterval has width 1 over n, okay? Now, our function is decreasing. And so they wanted us, if you remember, I can scroll back up for us if it helps. It says find the limiting value of lower sum. So they want us to use a lower sum. Remember, we can use an upper sum, a lower sum, or a midpoint sum. But they're being explicit as they want us to use a lower sum. So our function here is a decreasing function from 0 to 1. So we know that the smallest or minimum value in each subinterval will occur at the subinterval's right endpoint. And we discussed that in an earlier lesson. If they want us to find a lower sum, then we need to evaluate the function 1 minus x squared at the minimum value from each of these subintervals, which happens to be the right endpoint because this is a decreasing function. So our lower sum is constructed with rectangles whose height is determined by evaluating our function at the right endpoint from each subinterval. And of course, the width of each rectangle is 1 over n. So this is what we have then. It will be our function, I'll call our function f, which is 1 minus x squared, evaluated at that first right endpoint. So that's the height of the rectangle times the width of the rectangle, right? So this right here is the area of the first rectangle plus the height of the second rectangle times its width. So there's the area of the second rectangle plus, and then you would keep going, plus the kth rectangle would be k over n times 1 over n, right? Plus, etc. Plus, let me come down here, plus the nth, or the last rectangle, would be f of n over n, which is, of course, which is just 1, right? So f, our function evaluated at this right endpoint 1, which is n over n, times the width of that rectangle, which is 1 over n. All right, so these are all of the areas. These are the areas of each of our rectangles. All right. Now this is where sigma notation comes in, because, you know, this is kind of a pain to write. So let's see if we can use sigma notation to write this sum. So sigma notation would be the sum of, let's see, f of, I'm looking at this entire sum. So each one is f of these right endpoints, f of right endpoint, f of the right endpoint, f of the right endpoint. So then I can write it as f of k over n times the width of each of the rectangles, 1 over n. And I can let k go from 1 all the way to n. You see that? Now, remember that our function here is y equals 1 minus x squared. So each one of these right endpoints, when you evaluate f, our function, at k over n, it is 1 minus k over n squared, right, everybody? So which gives us the ability to simplify sigma notation here. So then this would be the sum of 1 minus k over n squared times 1 over n, as k goes from 1 to n. All right? So 1 minus k over n quantity squared, that was found by evaluating our function at k over n, which represents the right endpoint from each of our subintervals. All right, so let's continue simplifying. Let me get rid of this. And now we can write this sigma notation. We can continue. This is equivalent to the sum of let's see, so this is 1 minus k squared over n squared, right, times 1 over n. Okay, let's continue. So then this is equal to the sum of 1 over n minus k squared over n cubed. Put parentheses around this because it's the sum of all of this as k goes from 1 to n. Let's not lose our index of summation as we go through this. And this is equal to, using our rules, this is equal to the sum of 1 over n minus the sum of k squared over n cubed as k goes from 1 to n, of course. All right, so you continuing to use our rules, this is equal to n. So keep in mind, this expression here does not depend on k at all, so it's like our constant. So then this is n times 1 over n minus, we can pull out 1 over n cubed because that doesn't depend on k. So it's minus 1 over n cubed times the sum of k squared as k goes from 1 to n. Okay, let's continue simplifying. This is 1 minus 1 over n cubed. And this is the sum of the first n squares. So then this is equal to n times n plus 1. Remember, we wrote this down earlier. 2n plus 1, all of this over 6. All right, excellent. So let's continue simplifying. Let me use all of the board here, so I'm going to move this over if you don't mind. Is equal to 1 minus, let's expand this in the numerator. If you expand all of that in the numerator, you get 2n cubed plus 3n squared plus n all over 6n cubed. All right, we're just about there. Now we have now an expression for the lower sum that holds, that is true for any n, for any number n, for however many rectangles you wish to use. You want to use 4 rectangles like we did earlier. You want to use 16 rectangles, 20 rectangles, 200 rectangles, 1,000 rectangles. This expression will give you the lower sum. So what we're going to do now is evaluate the limit as n approaches infinity. What does that mean? We're using infinitely many rectangles. Infinitely many rectangles. Why? Well, the more rectangles we use, the more accurate our sum will be. So we are letting n approach infinity. Okay, so what is this? So the sum will be, let's see, this is just a constant, so this is just 1, minus, remember how to evaluate the limit. This is, let's divide each term by the largest power of the variable in the denominator, which is n cubed. So we did something like this. The limit as n approaches infinity of 1 minus the limit as n approaches infinity of 2n cubed over n cubed plus 3n squared over n cubed plus n over n cubed, all of that over 6n cubed over n cubed. Let's put all of that in parentheses. Okay, cool. So then this is 1 minus the limit as n approaches infinity of 2 plus 3, that's an ugly plus sign, hold on, plus 3 over n plus 1 over n squared over, yeah, we're good. All over 6. And so you can see this term here approaches 0 as n goes to infinity, and so does this term. So then this is just equal to 2/6. So then this is really exciting that we can now say that the lower sum is equal to 1 minus 2/6, which is 1 minus 1/3, which is, here's the lower sum, everybody, exactly equal to 2/3. This is the exact area for the region that we were considering that's underneath our curve. Isn't that amazing? So the lower sum approximations converge to 2/3. So this is amazing because earlier we were just approximating what that area would be, and we said soon we'll be able to say that or show that the sum is exactly 2/3. Now what's really interesting is that a similar calculation shows that the upper sum also converges to 2/3. Actually, any finite sum, your lower sum, upper sum, or even a midpoint sum, they're all going to converge to this same value, 2/3. Now, the theory behind all of this, the theory of limits, of finite approximations like we're using, is all due to a mathematician whose last name is Riemann. And so we want to introduce the notion, the idea of a Riemann sum now. That really just underlies the theory behind what we're using now. The idea of a Riemann sum is we start with an arbitrary bounded function named f on a closed interval from a to b. In this picture that we just made up here, this function may have negative as well as positive values. So we don't restrict our conversation to only functions that have positive values. We can look at functions that have negative values as well, okay? What we're going to do is we're going to, the same game, if you will, the same idea. We want to subdivide the interval from a to b. We want to subdivide this interval into subintervals. They don't necessarily have to have equal widths, by the way, but we want to subdivide this interval from a to b into subintervals, and we want to form sums in the same way we were doing it earlier for the finite approximations. Okay. So I can subdivide, let me move this up just a little bit. I can subdivide our interval from a to b in the following way. I can say, oh, I didn't mean to do that. Sorry. There we go. I can subdivide it like this. Here's our first subinterval, x naught, comma, x sub 1. That could be our first subinterval, where x naught is a. Okay, that's my left endpoint, which is a. And x sub 1 is somewhere around here, some value greater than a. That's one subinterval. The next subinterval would be x sub 1, comma, x sub 2. Our next interval would be x sub 2, comma, x sub 3, etc. Let me clean this up a little bit here. Just make sure it's really legible for you. Etc. until we get to x sub n minus 1, comma, x sub n. That would be the last subinterval where x sub n is equal to b. I can actually, I think I can make this really clear if I do it like this. If this is our interval from, here's our x-axis, okay? If this is our x-axis, if this is our interval from a, which is x naught, all the way to, make sure that looks like x naught, okay, all the way to b, which is x sub n. Then our first interval is from x naught to x sub 1. Okay, so this is our first subinterval. And then from, I'll draw a picture where these subintervals all have the same width, but that's not necessarily needed. The next subinterval would be x sub 1 to x sub 2. Right, so this is our second subinterval. Our third subinterval will be from x sub 2 to x sub 3, and so forth. Our kth subinterval will be x sub k minus 1. Let me see if I can make that nicer for you. To x sub k. Right? Because look at this. This is our second subinterval, and it starts with x sub 2 minus 1 to x sub 2. This is our second subinterval. This is our third subinterval, and look at it starts at x sub 3 minus 1, and then x sub 3. So if this is our kth interval, then it's x sub k minus 1 to x sub k, etc. until we get to the nth subinterval, which would be x sub n minus 1 all the way to x sub n, which is what we're calling b. okay? And so the width of our intervals would be delta x, and it is this here, that. And if each subinterval has the same width, then delta x is the same for all of them. It's a common width, right? So that would be delta x. This would be delta x. Let me see if I can read. There we go. This would be delta x. All of them would be delta x, right? Of course, it doesn't look like that's true here, but it's just because I messed up because of my drawing's a little sloppy. But I'm trying to draw it so they all have equal width. So delta x represents the width of each rectangle, the width of each subinterval. Okay. Now what we do is we choose a point from each subinterval. We choose a point from each subinterval, and we evaluate our function at that point. We can call that point c sub k. Sometimes, if you're calculating a lower sum and your function is decreasing on that interval, then the lower sum would mean that you are evaluating your function at the right endpoint. The upper sum would be evaluating your function at the left endpoint, right, of each subinterval if your function is decreasing. And then we already talked about how a midpoint sum would be taking the midpoint of the subinterval. But in either case, let's call c sub k that value, that point from each of the subintervals that you're evaluating your function at, which is giving you the height of your rectangles. So this summarizes our plan, our idea. In each subinterval, we select some point. The point chosen is called c sub k. Okay, c sub k represents the point that we are choosing from each subinterval to evaluate our function. We evaluate the function at this point called c sub k from each subinterval, and that's giving us the height of our rectangle. So we stand a vertical rectangle that stretches from the x-axis all the way to touching the curve, touching our function at this point, c sub k, comma, f of c sub k. This is the ordered pair at which the rectangle intersects our curve. Now, this point here can be below the x-axis or above the x-axis, right? So these rectangles can be above, or they could even be below the x-axis, depending on whether this function value is positive or negative. If it's equal to 0, then your rectangle is just right there on the x-axis, right? It's like it's a rectangle whose height is 0, you know. So let me take us back to our picture here. If I can do this in a neat kind of way. Yeah, here's our picture. Let me show you a picture of what we just said. So this is what we have. Notice that our interval from A, which is x naught, all the way to B, which is x sub n, has been partitioned or subdivided into subintervals. Here's the first interval from x naught to x sub 1, second interval from x sub 1 to x sub 2, the kth interval from x sub k minus 1 to x sub k, the nth interval from x sub n minus 1 to x sub n. From each of these subintervals, we are choosing a c sub k value. So this is c sub 1 from the first subinterval. And this is c sub 2 from the second subinterval, and so forth. And at each one of these c sub k values, we're evaluating our function at these points to determine the height of our rectangle. Now, f of c sub 1 is negative because it's below the x-axis. So this rectangle here shows below the x-axis. Again here, and then these rectangles are above the x-axis because f of c sub k, f of c sub n are positive. All right. Now, f of c sub 1, f of c sub 2, and so forth are negative. Therefore, this when calculating the sum, this is going to give us the negative of the area of a rectangle. Remember, area of an object like a rectangle must be positive. But because this is below the x-axis, this is going to represent the negative of, or the opposite of, the area of these rectangles. Okay? So this is what we get. We can write this as, we can sum all these products. I can move this up just a little bit. We can write this in sigma notation as the sum of f of c sub k, that's the height of each of your rectangles, times delta x sub k, right? As k goes from 1 to n. Remember, this right here is the height of the rectangle, and this here is the width of the rectangle. So this sum here is called the Riemann sum for this function f on the interval from a to b. Now remember, there are many sums that we can, use here. It depends on the choice for c sub k. You remember we looked at some examples in earlier lessons where we chose to evaluate our function at the left endpoint, or at the right endpoint, or the midpoint of each subinterval, right? That is to say, an upper sum, a lower sum, the midpoint, right? So this Riemann sum here can be written differently depending on our choice for c sub k for each of these points from each of the subintervals. In the case where each of these delta x, each of the subintervals have equal width, we can make these rectangles really, 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 really thin. I mean, that's hard for me to draw here, but imagine these rectangles being extremely thin and thinner and thinner and thinner. We can do that by increasing their number n. In other words, increasing the number of rectangles that we use. What did I draw here? 1, 2, 3, 4, 5, 6 rectangles. Imagine 60 rectangles or 600 rectangles. Imagine how hard that would be for me to draw, but imagine 6,000 rectangles. So the more rectangles I have, in other words, as I let n, the number of rectangles, approach infinity, these rectangles are becoming thinner and thinner and thinner, and my approximation, my sum, is becoming more and more and more accurate.